All right, let's talk about something that sounds like it's straight out of science fiction, but is very, very real: quantum computing. And I'm not just talking about a faster computer. No, this is a total rewrite of the rules of computation. It's a technology that's poised to change, well, pretty much everything.
So just to give you a sense of the sheer power we're talking about, think about the encryption that keeps all our digital lives safe. Our banking, our messages, everything. An ideal quantum computer could shatter those protections in just a few minutes. To put that in perspective, our most powerful supercomputers today would need thousands, maybe even millions of years to do the same thing. Yeah, the gap is that huge. And while we're not quite there yet, believe me, the race to build one is absolutely on. So how on earth is that even possible? Well, that's what we're going to break down. We'll look at the kinds of problems that even our best computers can't solve. Then we'll dive into what makes a quantum computer tick, going beyond simple zeros and ones. We'll talk about how you program with probability, how you actually find the right answer in all that chaos, and we'll even touch on that spooky connection that weirded out Einstein himself. And finally, we'll see what this all means for the future.
Okay, first up, why do we even need a whole new kind of computer? I mean, the ones we have are pretty amazing, right? But the thing is, for certain types of problems, they just hit a wall, a fundamental limit. And it's a wall built by the very laws of physics.
It all boils down to the most basic piece of information. You know how our regular computers use bits? They're like a light switch, either on or off, a 1 or a 0. Simple. But quantum computers use something called a qubit, and this is where your brain has to do a little flip. A qubit can be a 0, it can be a 1, or it can be both at the same time. It's not just on or off, it's like a dimmer switch, holding a whole range of possibilities all at once.
And that one little trick, being in many states at once, is the key to everything. It's what lets quantum computers take on problems that are just astronomically huge. We're talking about things like simulating the exact behavior of a molecule to invent a new drug, or untangling the mess of global supply chains, or building the next generation of AI. These are problems with so many moving parts that a normal computer, trying to check every option one by one, would literally be crunching numbers for longer than human civilization has existed.
All right, so let's dig into that first piece of quantum magic, this idea of being a 0 and a 1 at the same time. It has a name, and that name is superposition.
Yeah, so superposition means that instead of being locked into on or off, the qubit is in this kind of fluid state of probabilities. The light switch analogy just doesn't work here. The dimmer dial is much better. It's not just on or off, it can be any shade in between. And in a way, it's all of them simultaneously.
And this is where the mind-blowing power comes from. See, with every qubit you add, the number of possibilities you can explore doubles. So 2 qubits can check 4 states at once. 3 qubits can check 8. It doesn't sound like much, but this grows exponentially. By the time you get to just 300 qubits, you could represent more possible states than there are atoms in the entire known universe. Just let that sink in. No classical computer could ever do that.
Okay, so we've got these super powerful qubits that can hold a universe of information. But how do you actually use them? How do you write a program for something like that? You can't just tell it what to do. You have to kind of nudge its probabilities in the right direction.
The tools for the job are called quantum gates. Think of it like this. Your laptop uses logic gates, things like and, or, not, to flip its bits around. Well, a quantum computer uses quantum gates to do something similar, but instead of flipping a switch, they're carefully changing the probabilities of the qubits.
Let's take a famous example, the Hadamard Gate. It's one of the most fundamental ones. If you have a qubit that is sitting there, definitely in the 0 state, and you hit it with a Hadamard gate, poof! It instantly puts it into a perfect 50-50 superposition of both 0 and 1. It's like the starter pistol for a quantum calculation.
But wait a second, this brings up a huge, kind of obvious question, right? If the qubit is in this fuzzy, in-between state of being both 0 and 1, what happens when you actually try to read the answer? I mean, your screen can't show you a maybe, can it?
And this is where quantum mechanics gets really weird. The second you try to measure it, to look at it, the superposition is gone. It just vanishes. The qubit is forced to pick a side, and it collapses into a definite state, either a 0 or a 1. In our case, with that perfect superposition, it's a 50-50 coin toss which one you'll get. The very act of observing it changes the outcome. Wild, right?
Okay, hold on. If measuring it just gives you a random answer, what's the point? That sounds totally useless for, computing. How do we make sure that when the qubit finally picks a side, it picks the right one?
Here's the trick. Remember how the qubit is both 0 and 1 at the same time? When you apply a quantum gate, you're not just doing one calculation. You're doing the calculation on the 0 part and the 1 part simultaneously. With a bunch of qubits, you are literally exploring millions of pathways all at once. It's this massive, massive parallelism that gives quantum its edge.
But how do you sift through those millions of pathways to find the single right answer? This is where the next piece of the puzzle, called interference, comes in. Imagine each possible answer is like a wave rippling across a pond. A cleverly designed quantum algorithm makes the waves for all the wrong answers collide and cancel each other out. They just fizzle away. But the waves for the one correct answer, they all line up and reinforce each other, getting bigger and bigger. So by the end, when you finally take that measurement, the probability of getting the right answer is incredibly high. All right, we're on to our last major quantum concept, and this is probably the weirdest one of all. It's the one that Albert Einstein himself famously called spooky action at a distance. We're talking about entanglement.
So entanglement is what happens when you link two qubits together so tightly that they basically become a single entity. Their fates are intertwined. And here's the spooky part. No matter how far apart you pull them, even if they're on opposite sides of the galaxy, they stay connected. If you measure one, you instantly know the state of the other. Instantly.
So let's say you have two entangled qubits. If you measure the first one and it turns out to be a 0, you know with absolute 100% certainty that its partner, wherever it is also a 0. Same thing if it's a 1. You'll never ever get a mismatch where one is a 0 and the other is a 1. They act as one, perfectly in sync.
So there you have it, the big ideas. Superposition, quantum gates, interference, and entanglement. Let's put all those pieces together now and talk about what this new computing era really means for all of us.
I mean, just think about it. The phone in your pocket right now has way more computing power than all of NASA had when they sent people to the moon. That was a huge leap. Quantum computing is the next leap. And it's not just about making things faster. It's a completely different, fundamentally new way to compute.
So let's just quickly run through the quantum toolkit one more time. You've got superposition, which lets you explore a massive number of possibilities all at once. You have interference, which is the clever trick to weed out all the wrong answers and boost the right one. And you have entanglement, which creates these powerful connections between qubits. Put them all together and you get a machine that can solve problems that our current computers wouldn't be able to solve in the lifetime of the universe.
And we're not just talking about abstract math problems here. This power is going to lead to some incredible real-world breakthroughs. Imagine being able to design new life-saving medicines by perfectly simulating molecules, or building financial models that can actually predict and prevent economic crashes, or creating artificial intelligence that's powerful in ways we can't even imagine yet. This isn't just about making things a little bit better, it's about doing things that were previously thought to be impossible.
Look, we are standing right on the brink of this new age. The hardware is getting better and better every single day. And that quantum advantage is coming into focus. So really, the question isn't if this is going to change the world. It's how it's going to change it. So I'll just leave you with this to think about. What's the first impossible problem you'd want us to solve?